Welcome to the Cabinet of Science and Fiction.
Today, we're definitely opening the cabin on something special. One of the biggest dreams from sci-fi, really. The warp drive.
Yeah, exactly. We're trying to move past, just the cool visuals on screen and really dig into the physics, the actual mathematical possibilities of bending space-time.
That's the plan. So, if you're prepping for that advanced propulsion meeting, or maybe just trying to keep up with where general relativity is heading.
Or maybe you're just fascinated, like us, by the idea of finally crossing those huge cosmic distances. Well, this is your deep dive. We're zeroing in on the Alcubierre drive and all the really interesting, sometimes pretty wild concepts that have spun out from it since '94.
Right. And our mission today really is to try and synthesize all this complex physics, the engineering challenges too, that come with warping spacetime for, well, hyperfast travel.
And we're grounding this conversation in solid sources. We've looked at the original work by Miguel Alcubierre himself, of course.
Absolutely. And then there's crucial research from universities like the University of Alabama in Huntsville, Catholic University of Pleven over in Belgium, the University of Oxford.
And naturally, the groundbreaking stuff from Dr. Harold White and his team at NASA EagleWorks, plus some more recent updates from researchers like Eric Lentz and Jamie Farnes. It's a rich field.
It really is. So the goal for you, the listener, is to walk away with a clear picture, kind of a structured understanding of how this research has unfolded.
Yeah, basically the three main phases. The initial, wow, this is impossible energy requirements.
Right, the big numbers.
Then the decades spent trying to shrink those numbers down, find clever workarounds.
Rhythm optimization phase, yeah.
And now this newer push into maybe positive energy solutions and even starting to think about actual experiments.
We want you to see how science is tackling this piece by piece, trying to move the warp drive from just, a cool idea in Star Trek
to something theoretically sound and maybe, just maybe, experimentally verifiable down the line. Calculated, step by calculated step.
So let's start with the why. Why bother with physics this exotic?
It really comes down to the sheer scale of space, doesn't it? Conventional methods just don't cut it.
Yeah, the scale is the fundamental problem. It makes even our fastest spacecraft seem, well, practically stationary when you look at interstellar distances.
It's hard to grasp those light-year numbers. They feel abstract, so let's anchor it. Voyager 1, that's a real thing out there right now.
Good example. Voyager 1 launched way back in 1977. Still holds the record, right? Highest energy launch we've managed for a probe leaving the solar system.
Tiny thing, too. Less than a metric ton.
Yeah, about 0.722 metric tons. Designed for the outer planets and the edge of interstellar space. And after all these decades, it's moving at about, 3.6 astronomical units per year?
An AU being Earth-Sun distance, roughly 93 million miles.
Right. Now compare that to Alpha Centauri, our closest star system neighbor. 4.3 light years away. Seems close on a galactic map, maybe?
But in AUS.
It's a killer. That translates to, let me check the number, 271,931 AU. So if Voyager 1 was pointed straight at it, which it isn't, but if it were, you're looking at roughly 75,000 years to get there.
75,000 years.
And remember, nothing we've launched since is expected to ever catch up to it. So conventional speed, interstellar travel is basically a multi-millennial project.
Your, 3,000th great-grandchild might see the arrival photos. Maybe.
Exactly. It makes things like budgets and logistics seem almost quaint by comparison.
So the only way around that, sticking with known physics and rockets, is just brute force. Which brings us to a Project Daedalus, that 1970s study.
Yes, Daedalus. A serious attempt by the British Interplanetary Society. They wanted to design a probe, robotic, that could reach Barnard's star about 6 light years away in 50 years.
50 years. Still long, but, within a human lifespan, potentially. What did that brute force approach look like?
It looked immense, almost absurdly so. The final concept, a spacecraft weighing 54,000 metric tons.
54,000. Okay, context. The International Space Station is...
The ISS is around 450 metric tons. So Daedalus would have been well over 100 times heavier.
That's like launching a battleship, basically.
Pretty much. And the kicker, most of that mass, 92% of it, was just fuel.
Fuel for what?
Specifically, deuterium and helium-3 for a massive nuclear pulse propulsion system. Essentially, setting on contained fusion bombs behind you over and over.
Wow. A giant, flying, fusion bomb-powered engine just to get a small probe 6 light years away in half a century.
That's the brute force solution.
Okay, so option A, wait 75,000 years. Option B, build a 54,000-ton fusion bomb ship that still takes 50 years.
No, I know.
Neither sounds great for, actually exploring or settling space.
Not really practical, no.
Which leads us to that big question physicists started grappling with. Is there another way? Can we cheat distance without actually breaking the local speed of light limit?
Come on. And that's the pivot point. We stop talking about bigger rockets and more fuel, and we start talking about, well, space-time engineering, playing with the fabric of reality itself.
General relativity territory.
Exactly. And GR gives us, broadly speaking, two theoretical paths around the speed limit problem.
Path 1 is the sci-fi favorite, the shortcut.
That's the wormhole, yeah. The Einstein-Rosen bridge. Hypothetical tunnels connecting distant points in space-time, like folding space over and poking a hole through.
But they come with their own big issue, right? Stability.
Mm-hmm. Keeping the throat of the wormhole open is the problem. People like Kip Thorne showed you'd likely need something called exotic matter stuff with negative energy density just to prop it open against gravity trying to slam it shut instantly.
Okay, so wormholes need exotic matter. What's path 2, the one we're focusing on today?
Path 2 is space warps. Instead of tunneling through space-time, you manipulate space-time itself around your ship. You compress it in front, expand it behind.
So you're surfing on a wave of space-time.
That's a good way to put it. And this idea, manipulating the fabric of space, leads us directly to the foundational work here, the Alcubierre metric.
And it's fascinating, isn't it, that the inspiration wasn't some obscure mathematical problem, but straight out of pop culture.
Oh, absolutely. You can't really talk about the Alcubierre drive without mentioning Star Trek. While the term warp drive goes way back, John W. Campbell in the 30s.
Right. Islands of space?
Yeah. But when Miguel Alcubierre, the Mexican theoretical physicist, published his paper in '94 in Classical and Quantum Gravity, he literally cited Star Trek's warp drive as the thing that got him thinking. He asked, could the physics actually allow for something like this?
Amazing. Sci-fi sparking real physics.
Yeah.
So let's break down his solution, the Alcubierre metric. What is it at its core?
At its core, it's a specific solution to Einstein's field equations. It describes a particular geometry of spacetime, what physicists call a Lorentzian manifold, that allows for a sort of localized bubble, a distortion, to form in flat space and then move off potentially faster than light.
Okay, a warp bubble. How does it work? You mentioned compressing and expanding space.
Exactly. Think of it like this. The space right in front of the bubble is intensely contracted, like squeezing an accordion. Makes the distance to your destination effectively shorter from the bubble's perspective. And simultaneously, the space directly behind the bubble is rapidly expanded, pushing it forward away from where it started.
So the ship inside isn't actually moving through space in the traditional sense?
Precisely. The ship, or whatever's inside the bubble, is just sitting there in a cozy little patch of flat space-time. It's an inertial reference frame. It's the bubble itself, the distortion, that's moving. The ship gets carried along, like a surfer on a wave or someone on a moving walkway at the airport.
Oh, okay. And that's the clever bit that gets around the speed of light limit, because the ship locally isn't breaking season.
That's the crucial point. Inside the bubble, you're not accelerating past light speed relative to your immediate surroundings. You're always subliminal locally. It's the coordinate speed, the speed measured by someone far away, like back on Earth, that can exceed season. The bubble itself is moving the space, and the expansion of space itself isn't limited by season.
So general relativity is satisfied, technically. That sounds like the perfect ride for astronauts.
From the inside, it seems amazing. One of the really appealing things is that the proper acceleration, the g-forces you'd feel, is technically zero.
No kidding, 0 Gs, even while traveling FTL.
0 Gs. You're in free fall, inside that flat space bubble. The space outside is doing all the work.
Wow. Okay. And what about time dilation? Usually, going your light speed messes with clocks.
That's another plus. Alcubierre's math showed that clocks inside the bubble would tick at the same rate as clocks far away, like at mission control. Your proper time equals their coordinate time.
So a trip to Alpha Centauri takes, say, a few weeks for the crew.
And it also takes a few weeks for everyone back on Earth.
Yeah.
No weird time differences like in conventional relativistic travel. It's the dream scenario for interstellar travel, really.
Okay, it sounds too good to be true. There has to be a catch. And it's a big one, isn't it? The energy source.
The nightmare lurking behind the dream. To make this metric work, specifically to get that space-time contraction in front of the bubble, the energy density required turns out to be negative.
Negative energy density, sometimes called negative pressure. Right? What does that actually mean?
It means you need exotic matter. This is the big hurdle.
And exotic matter isn't just like antimatter or something slightly unusual.
No, it's fundamentally different. It's hypothetical stuff whose stress energy tensor violates certain fundamental assumptions we usually make about energy and matter, things called the energy conditions, like the null, weak, and dominant energy conditions.
And what does violating those mean physically?
Basically, it would have repulsive gravitational effects. It would push space-time apart instead of pulling it together like normal mass energy does. Classically, it's considered non-physical.
But not strictly ruled out. I remember Alcubierre himself suggested maybe the Casimir effect.
He did. The Casimir effect, the quantum vacuum energy between two closely spaced plates, does theoretically have a negative energy density. But the amounts are incredibly tiny, and harnessing enough of it, stabilizing it for a warp bubble. That's a monumental, perhaps impossible engineering challenge.
And the initial estimates for how much negative energy you'd need, those were the real shocker, weren't they?
They were terrifying. The first calculations for a reasonably sized bubble-moving FTL required negative energy equivalent to the mass of the entire observable universe.
The entire universe.
Yeah. So you have this beautiful, elegant mathematical solution, powered by an impossible amount of physically questionable energy. That set the stage for decades of follow-up research. Can we keep the cool space-time trick, but somehow drastically reduce or even eliminate that insane energy requirement? #UpIV. The battle against massive energy requirements, yeah, those initial numbers were just crushing. Michael Fenning and Alan Everett did some early rigorous calculations. For just a small ship, maybe going 10 times the speed of light, they figured you'd need negative energy equivalent to minus 10 to the power of 64 kilograms.
Minus 10 to the 64, that's a negative number with 64 zeros after it. How does that compare to, say, the mass of the universe?
It's orders of magnitude more negative than the positive mass we estimate exists in the entire observable universe. So, yeah. Deeply discouraging.
And it wasn't just the sheer amount, right? That it was also a problem with how thin the structure had to be, the wall thickness problem.
Exactly. For the bubble to actually achieve faster than light travel, the calculations showed the region containing this exotic matter, the bubble wall had to be incredibly thin. We're talking about 1032 meters thick.
10 to the minus 32. That's tiny. Isn't that around the Planck length?
Perilously close, yeah. The Planck length is sort of the fundamental pixel size of space-time in quantum gravity theories. Trying to engineer structures that thin is way beyond anything we can currently conceive of. So even if you had the negative energy, building the bubble itself seemed impossible.
Okay, so the challenge was twofold. Ridiculous energy amounts and impossibly thin structures. How did researchers start tackling the energy problem first?
The first big conceptual leap came from Chris van den Broek over at Catholic University Leuven in '99. He realized the problem wasn't just the total energy, but how it was distributed, particularly across the bubble surface.
So he played with the geometry.
He did. Instead of a simple sphere, he proposed a clever trick. Contract the surface area of the bubble on the outside while simultaneously expanding the volume inside the bubble.
Ah, right. The TARDIS configuration. Smaller on the outside, bigger on the inside. How does that save energy, though? It sounds counterintuitive.
It does, but the negative energy is mostly needed right at the surface to create that warp effect. By shrinking the external surface area where the exotic matter density is highest, while puffing up the internal volume where the ship sits, van den Broek found he could dramatically reduce the total amount of negative energy required. It's about minimizing the surface tension, effectively.
And did it work? How much did it reduce the requirement?
It was a massive improvement. It brought the energy needed down from mass of the universe to something like less than 3 solar masses of negative energy.
Okay, 3 solar masses is still huge, but compared to the universe.
It's a colossal reduction. Then Sergei Krasnikov came along in 2003 and tweaked the van den Broek metric slightly, suggesting you could potentially get the required negative mass down to just a few milligrams.
Milligrams. Now that sounds almost doable.
Well, theoretically, yes. But van den Broek himself pointed out the catch. Even if you only need milligrams in total, the density required packing that negative energy into that tiny Planck scale thick wall was still astronomical. The engineering challenge of achieving those densities and structures remained.
Right. So less total stuff, but packed incredibly tightly. Which leads us to Dr. Harold Sonny White at NASA Eagle Works. His work really shifted the focus again, didn't it?
Yeah.
Towards making the requirements seem, well, maybe not easy, but less impossible.
Dr. White's work, especially in his Warp Field Mechanics 101 and 102 papers, was really focused on optimization through geometry, but in a different way than Vandenbroek. He looked at the shape of the exotic matter region itself.
Instead of just a super thin shell.
Exactly. He proposed changing that thin ring into a thicker, sort of fuzzier torus, like a donut shape surrounding the ship.
Okay, why a donut? What's the physics advantage there?
It's about spreading the load, essentially. By making the region of negative energy density thicker, distributing it over a larger volume, you reduce the peak density required at any given point. You might sacrifice a tiny bit of the perfectly flat space inside for the ship, but the overall energy cost drops significantly.
It makes the requirements less extreme at any one spot.
Precisely. It's a trade-off between peak density and total energy, and the math showed this torus topology was way more efficient.
And what did this do to the total energy needed? This is where the numbers got really interesting, right?
This was the breakthrough that got a lot of attention. White's calculations suggested that changing the topology to this torus shape could reduce the required exotic mass energy for a decent-sized ship, say 10 meters across, from the equivalent mass of Jupiter.
Still huge.
Down to the equivalent mass of the Voyager 1 probe, about 700 kilograms, maybe even less.
Wow. From Jupiter down to Voyager.
Yeah.
That's a game changer, psychologically at least. Suddenly it's in the realm of something you could conceivably power, maybe with a very advanced fusion reactor, not needing a whole planet's worth of exotic stuff.
Exactly. It put the energy requirement for the very first time into a range that felt almost tangible. Still incredibly difficult, but not fundamentally astronomical.
And he had another trick too, right? Something about oscillating the field.
Yes, he noted that by dynamically oscillating the intensity of the space warp over time, you could potentially reduce the energy requirements even further. Especially, he suggested, if you start considering higher dimensional models, which adds another layer of complexity and potential optimization.
And speaking of connections, there's even newer research linking these warp bubbles to things that already exist in space, like strong gravity fields.
Right. That 2024 study by Garatini and Zatromailov is fascinating. They explored what happens if a warp bubble isn't just an empty flat space, but is moving through an existing strong gravitational field.
Like near a black hole or something.
Yeah.
How would that help reduce the need for negative energy?
The idea is that the intense curvature of space-time already present near a massive object contributes some of the necessary stress energy conditions for the warp effect. The ambient gravitational field sort of pre-warps the space a bit.
So the warp drive doesn't have to do all the heavy lifting itself.
Potentially, yes. It might only need to supply the additional stress energy needed to push the bubble past the speed of light, which could be significantly less than starting from scratch in flat space. It's an intriguing idea connecting warp drive theory to the most extreme environments we know of.
Okay, reducing the amount of negative energy is one thing. Getting it down from Jupiter to Voyager mass is huge. But the ultimate dream would be to get rid of the need for this exotic negative stuff altogether, right? Is that even on the table?
For the longest time, most physicists would have said, probably not. The math seemed pretty clear. You needed that negative energy density for the Alcubierre metric to work as originally proposed. But then, in 2021, things got really interesting.
What happened?
A physicist named Eric Lentz, working out of the University of Göttingen, published a paper describing a new class of solutions. He called them hyperfast solitons, basically, warp bubbles, but sourced entirely from known familiar forms of purely positive energy.
Whoa, hang on. Positive energy? Like normal matter in fields. No exotic stuff needed at all.
Exactly. That was the bombshell. His model uses complex configurations of conventional energy and matter fields, essentially creating a stable shell of positive energy density that generates the necessary shift vectors to mimic the Alcubierre effect, but without violating those energy conditions.
That fundamentally changes the game, doesn't it? If Lentz is right, the warp drive isn't mathematically tied to hypothetical negative energy anymore.
It completely reframes the problem. It shifts it from needing impossible matter to needing, well, potentially just immense amounts of possible energy.
There's always a catch. What's the trade-off here? If you use positive energy, how much do you need?
The trade-off is that the energy requirements shoot back up again, dramatically. While Lentz's approach solves the type of energy problem, no more exotic matter, the sheer quantity of positive energy needed is still huge, back on the order of the mass of Jupiter, roughly.
Okay, so we swap needing 700 kilograms of impossible stuff for needing a Jupiter mass of possible stuff.
Pretty much. Other researchers like Fell and Heisenberg have explored similar positive energy warp solutions, confirming it's a theoretically valid path. It means we might be able to build one without discovering brand new physics about negative energy, but the engineering challenge of manipulating Jupiter levels of energy remains immense.
Still, it's a massive theoretical step. It proves feasibility within known physics, even if the scale is enormous. Now, you mentioned Harold White looking at higher dimensions earlier. If manipulating space-time in our familiar 3+1 dimensions is so energy-intensive, can looking outside our dimensions help?
That's another really fascinating avenue of research. Dr. White, along with Eric Davis, explored this in the context of brain cosmology.
Okay, brain cosmology, give us the nutshell version.
The basic idea is that our universe, the one we experience with 3 space dimensions and 1 time dimension, might just be a brain, like a membrane or a sheet floating within a higher dimensional space called the bulk.
So, extra dimensions we can't normally see or interact with.
Kind of. Gravity might be able to leak into these extra dimensions, but we, and most forces, are stuck on the brain.
So how does this hidden bulk help us with warp drive energy?
The thinking goes like this. The stiffness of space-time on our brain, how much energy it takes to warp it, is related to fundamental constants, including the gravitational constant g. It's very stiff, requires huge energy.
Right, big number.
Exactly. But in some of these higher dimensional models, like the Chung-Freeze metric they looked at, if you can somehow manipulate or leverage effects from that extra bulk dimension,
Like, reach into the bulk somehow.
or influence the geometry through the bulk, the effective stiffness of space-time, as experienced on our brain, could potentially be reduced. It's like finding a way to make space-time softer from our perspective, but using the physics of the hidden dimensions.
So by tweaking things in the extra dimension, you make warping space in our dimension require less energy.
That's the theoretical possibility.
Mhm.
Couple that with White's idea of oscillating the warp field intensity, and the models suggest you could potentially get a significant reduction in the energy needed for FTL because the fundamental cost of warping space has been lowered by exploiting the higher dimensional physics.
Very speculative, but very cool. Okay, so we have positive energy solutions, maybe higher dimensions. But let's circle back to that original problem.
Yeah.
Negative energy or negative mass. Is there any hint from cosmology that something like this might actually exist out there?
Well, this is where warp drive theory potentially connects to some of the biggest mysteries in physics today. Dark matter and dark energy. There's a theory proposed by astrophysicist Jamie Farnes at the University of Oxford that tries to unify dark matter and dark energy into a single phenomenon, a dark fluid.
Okay.
And the key component of his model, it relies on the existence of negative masses that are gravitationally repulsive.
Negative masses. That sounds an awful lot like the exotic matter needed for the Alcubierre drive.
It sounds exactly like it, just on a cosmic scale. Farnes argues in his work, published in Astronomy and Astrophysics, that this negative mass fluid could explain galaxy rotation curves,
Yeah.
usually attributed to dark matter, and the accelerating expansion of the universe, usually attributed to dark energy.
So if his theory turned out to be right,
It would imply 2 huge things. 1, it might solve the dark matter-dark energy puzzle. And 2, it would mean that the kind of physics needed for an Alcubierre drive gravitationally repulsive negative mass actually exists in the universe, naturally and abundantly. He even pointed out Einstein himself briefly considered negative masses back in the day.
wow. So the feasibility of warp drive might actually hinge on solving the nature of 95% of the universe's energy density.
It's a potential link, yes. Highly debated, of course. Farnes' theory challenges the standard cosmological model, but if it holds up, it provides a natural source for the exotic physics the warp drive seems to demand.
We've spent a lot of time on the energy problem, and the progress there is fascinating. But energy isn't the only hurdle. There are some really deep fundamental problems with the warp drive concept concerning things like causality, control, and what happens when you actually arrive somewhere?
Absolutely. Let's start with the causality issue, which Sergei Krasnikov really brought into focus.
This has to do with the pilot inside the bubble being cut off, right?
Exactly. Remember, the ship inside is in its own little bubble of flat space-time, an inertial frame. It's causally disconnected from the bubble's leading edge, especially if the bubble is moving FTL. Signals from inside can't reach the front of the bubble to affect it.
So the pilot literally can't steer, or, more importantly, can't turn the drive off when they get close to their destination.
Pretty much. They can't send a signal forward faster than the bubble itself is moving. But the bigger issue Krasnikov raised is about creating the warp field in the first place. If you need exotic matter, or even just the massive positive energy for Lens's drive, how do you get it ahead of the ship along its path?
You'd have to pre-place it.
That's the argument. If you can't generate the fields instantaneously from the ship itself, you need infrastructure. Alan Everett and Thomas Roman pointed out the absurdity. To make a trip to a star 2,600 light-years away and arrive in less than 2,600 years, someone would have had to start laying down that warp field infrastructure 2,600 years ago.
It's like needing to build the railway tracks before the train can run, but you need the train to lay the tracks ahead of itself.
Precisely. D.H. Kuhl put it bluntly. Constructing a warp drive requires having already used a warp drive. It suggests FTL travel might only be possible along pre-established routes.
Unless you can generate the field entirely from the ship, instantaneously converting that Jupiter mass or 700 kilograms of exotic stuff into the field on demand.
Which is its own enormous physics and engineering challenge, maybe even harder than finding the energy in the first place.
Okay, let's imagine we solve causality. Maybe we figure out instant field generation. What about just surviving the ride inside the bubble? You mentioned control issues, but are there physical dangers too?
Notario pointed out the steering problem, but a more fundamental issue was raised by Barcelo, Finazzi, and Liberati. They looked at it using quantum field theory in curved spacetime.
And what did they find?
They found that for superluminal speeds, the intense space-time curvature at the bubble walls would essentially behave like a black hole event horizon from the perspective of quantum fields. This would generate intense Hawking radiation inside the bubble.
Hawking radiation, like black holes emit.
Exactly. The vacuum itself would heat up to potentially extreme temperatures. Their calculations suggested this thermal bath could destroy anything inside the bubble crew, equipment, and likely destabilize the bubble structure itself.
So it's not just zero Gs, it's potentially getting cooked by quantum effects.
Potentially, yes. Though they did note this specific problem seems to go away if the bubble stays strictly subluminal, which is another strong argument for focusing on slower-than-light applications first.
Definitely makes subliminal seem safer. But, okay, let's talk about the really scary one, the killer downside. What happens at the destination?
Yes. This is the consequence highlighted by Brendan McMonagle, Geraint Lewis, and Philip O'Byrne. It's sobering.
What do they figure out?
They realized that as the warp bubble travels, especially at FTL speeds, it doesn't just pass through interstellar space cleanly. It interacts with any particles it encounters: gas, dust, cosmic rays.
Like a stoop.
Kind of like a cosmic snowplow, yeah. These particles get trapped, accumulating against the forward edge of the bubble, riding along with it. They can build up over the entire journey, potentially light years worth of interstellar debris.
Okay, so you arrive with a bunch of space dust stuck to the front. So what?
So what happens when you decelerate? To stop, the warp field has to dissipate. And when it does, all those accumulated particles, which have been effectively carried along at superluminal speeds relative to the destination frame, are suddenly released. All at once.
Released with a lot of energy.
An insane amount of energy. Because they were moving so fast relative to the destination, their energy gets incredibly blue-shifted upon release. Their wavelengths compress, frequency spikes. Meaning, according to McMonagle and colleagues, the deceleration releases a blast of gamma rays and high-energy particles potent enough to essentially blast into oblivion anything directly in front of the ship.
Oblivion. Like destroy the target planet.
Potentially, yes. You arrive at your pristine exoplanet destination, switch off the warp drive, and instantly sterilize it with an infinitely blue-shifted particle beam made from all the dust you pick up along the way.
Good grief. So the act of arriving destroys the destination. That completely changes the ethics of interstellar travel, doesn't it?
It makes the warp drive potentially the most powerful weapon imaginable, even if used unintentionally. It's a huge, huge problem that needs a solution before anyone seriously considers FTL travel.
Okay, so we've got causality loops, potential quantum incineration, and accidental planetary destruction. Given all these massive, frankly, terrifying hurdles for FTL, where does the research realistically go next? Seems like aiming straight for starships is ambitious.
Extremely ambitious. And that's why the focus for many, particularly Dr. Harold White, has shifted towards exploring subliminal applications first, maturing the technology in our own backyard, so to speak.
Subliminal warp. How does that help if you're not breaking the light barrier? What's the advantage inside the solar system?
The advantage is all about efficiency. specifically reducing transit times and fuel requirements for conventional deep space missions, even below light speed.
Wow.
Well, think about propulsion systems. Their performance is often measured by specific mass, basically, how much mass the engine has to push for a given power level. Lower specific mass means faster acceleration and shorter trips.
Right. Wet mass divided by power level.
Exactly. Now, imagine you have a spacecraft, maybe 5,000 kilograms, with a good 100 kilowatt electric propulsion system, like a Hull thruster. That might give you a specific mass of 50 kilograms per kilowatt.
Okay. And a trip with that system, say, from Earth orbit to the Earth-Moon L1 point.
Might take around 70 days, typically. Now, what if you add a modest subluminal warp drive system to that spacecraft?
What does the warp drive do in this subluminal case?
It doesn't create an FTL bubble, but it generates that region of negative pressure or negative energy density. Even a small amount of this effectively acts like negative mass in the spacecraft's total mass budget.
So it makes the ship effectively lighter.
Precisely. Let's say the subliminal warp system generates an effect equivalent to negative 2,000 kilograms when it's active. Your 5,000 kilogram ship now effectively only weighs 3,000 kilograms as far as the thruster is concerned.
Ah, I see. So the specific mass drops.
Right. It drops from 50 kilogram hour down to 30 kilogram hours. And what does that do to the LEO to L1 trip time?
It should shorten it significantly.
Calculations suggest it could reduce the transit time from 70 days down to maybe 40 days.
Wow, saving 30 days on a trip just to the moon's vicinity? That's huge for logistics, fuel savings, crew exposure.
Exactly. It makes inner solar system travel much faster and more efficient. It proves the technology could be incredibly useful, revolutionary even, without ever needing to achieve FTL speeds or face those extreme relativistic problems.
It becomes a powerful booster engine, essentially.
In a way, yes. It allows you to mature the engineering, understand the field generation, the power requirements, all in a much less demanding subliminal context. If you could ever generate negative mass approaching the ship's positive mass, your effective mass nears zero, and transit times become incredibly short, even while staying below city dollars.
Okay, that makes sense as a development path. But how do we even start testing this? We need experiments. Which brings us to the White Judy Warp Field Interferometer at NASA Eagle Works. This is where the theory meets the lab bench, right?
This is the crucial step, yes, trying to bridge that huge gap between the mathematical equations and physical reality. The device Harold White designed with Richard Judy is essentially a very, very sensitive interferometer.
Like the Michelson-Morley experiment that tested for the ether.
Similar principle, but modified and far more sensitive. It uses a Hine laser, around 633 nanometers, splits the beam, sends the two beams along slightly different paths, and then recombines them.
And what are they hoping to see?
But they're looking for tiny, tiny shifts in the interference pattern when the beams recombine. The idea is to try and create a microscopic distortion of spacetime in the path of one of the beams.
A tiny warp bubble. How do they try to make that?
They use a high-voltage device specifically shaped as a torus, that donut shape again made of capacitors. The goal is to generate an electric field intense enough to slightly perturb the vacuum energy, creating a minuscule reach of negative pressure, effectively warping spacetime just a tiny bit.
How tiny are we talking?
They're aiming to perturb the optical index of the vacuum, how fast light travels through it, by maybe 1 part in 10 million.
1 part in 10 million. That sounds impossibly small to measure.
It is incredibly challenging, but if they can detect that minuscule induced phase shift between the laser beams when the device is active, that would be monumental.
Why? What would it prove?
It would be the first experimental evidence that we can actually engineer space-time geometry, even on a microscopic scale. It would validate the core physical principle behind the warp drive, the possibility of generating that negative pressure field in a lab. It moves it from pure theory towards potential engineering.
Okay, so experiments are starting. What about the theoretical side? You mentioned the equations are incredibly complex. How is that being handled?
Yeah, you can't just solve these things with pen and paper easily. Einstein's field equations are notoriously complex, nonlinear partial differential equations. Simulating dynamic warp drive spacetimes requires serious computational power and sophisticated numerical relativity techniques.
Which is where tools like the Warp Factory come in.
Exactly. Developed by the team at Applied Physics, Warp Factory is essentially an open-source software toolkit designed specifically for this problem. Think of it as a virtual wind tunnel for warp drives.
A virtual wind tunnel. What does it let researchers do?
It lets them computationally generate, model, and analyze different warp drive space-time geometries much more quickly and efficiently. They can plug in different parameters, different energy distributions, and see if the resulting space-time satisfies Einstein's equations, check the energy conditions, visualize the effects.
So it speeds up the design and testing process dramatically.
Hugely. It allows physicists to iterate on designs, test new ideas, and refine the theoretical models much faster than before, helping to zero in on potentially more efficient or stable configurations.
And this computational work is also revealing connections to other fields, like hypersonic flight.
There's some interesting conceptual overlap being explored there, yeah. Sometimes called the Davis drive, after Eric Davis. The idea is that the extremely hot ionized plasma generated around a vehicle during hypersonic flight,
Like on re-entry or future hypersonic planes.
shares some physical characteristics with the kinds of high-energy density plasmas envisioned in some warp drive models that might generate negative pressure effects.
So research into managing hypersonic plasma could potentially inform how we might create or manipulate warp fields.
It's a possible synergy. Understanding how those extreme plasmas behave might offer clues, or perhaps the plasma itself could even play a role in future systems, maybe as part of the field generation mechanism at very high, though still subliminal, speeds. It shows how interconnected advanced physics research can be.
Wow, what a journey. We've gone from Miguel Alcubierre's initial mind-bending 1994 paper elegant math, but needing universe levels of exotic energy.
Through decades of brilliant theoretical work, especially by people like Vandenbroek and Harold White, using geometry and topology to wrestle those energy requirements down, down, down.
From the mass of the universe to Jupiter, eventually down to the mass of Voyager 1, just 700 kilograms or so of that exotic stuff, making it seem, well, less impossible.
And then the recent breakthroughs, like Eric Lentz showing a path using only positive energy, which removes the need for undiscovered physics, even if it brings back the massive energy scale problem for FTL.
Plus, we're now seeing the first real experimental steps, like the weight-Jude interferometer, trying to detect even the tiniest flicker of engineered space-time distortion in the lab.
And the development of powerful computational tools like Warp Factory, essential for modeling these incredibly complex scenarios and designing more efficient drives.
So the big challenges remain. Can we actually source or create negative energy density, perhaps confirming ideas like Jamie Farns's dark fluid? Can we solve the causality and control paradoxes for FTL? And can the experiments actually detect anything?
We've definitely moved the needle, though. From pure sci-fi speculation to rigorous theoretical physics, and now dipping our toes into experimental validation. It's a testament to pushing the boundaries of what we think is possible.
But it's also, as we discussed, a field fraught with some deeply concerning potential consequences, especially that destination problem.
Which really brings us to that final thought, something for you to ponder. If we do crack it, if the next breakthrough, maybe even just for efficient subliminal travel, proves we can effectively negate mass or warp space controllably.
What's the ethical burden then?
What ethical responsibility do we have right then and there to confront and solve that killer downside, the potential annihilation of wherever we're going before we even dream of building the first true interstellar warp ship?
We might solve the physics of getting there, only to create an ethical nightmare upon arrival. A heavy thought.
A very heavy thought. It shows that progress in physics often raises equally profound questions about responsibility.
Indeed. Well, thank you for taking this deep dive into the physics and, yes, the philosophy of warp drives with us today.
We hope this gave you a clearer sense of the incredible work being done, turning maybe the biggest dream of science fiction into actual testable science, one equation, one simulation, one laser beam at a time.
Thanks for listening.
Until next episode.